Now let's take a look at approximating or representing functions with power series. So I've got here some various functions, and we want to uh, just recall power series representations of these functions. First of all, this one, 1 over 1 minus x. Remember, this one is x to the n and goes from 0 to infinity. And the radius of convergence is going to be 1. So the radius of convergence, we say x, the absolute value of x has got to be less than 1. It converges between -1 and 1. So if we choose x to be anything in that interval, then it will converge. That series will converge to that function, 1 over 1 minus x. The next one is like it, except we go from n equals 0 to infinity, and this is alternating. And it still has the same radius of convergence. X has got to be less than 1. Okay. Then we come over here. Now, this one, this 9c, we've got 1 over 1 plus x squared. It's like the 1 over 1 plus x. Now, by the way, we could go back and we could rederive these. These are just things that I'm thinking for the final you need to have in your mind. Okay, and because we're going to make changes, like for example, this 9c, 1 over 1 plus x squared. Well, we're just going to take the series, the 1 over 1 plus x, and replace the x with an x squared. So this is x to the 2n. And still, the radius of convergence is x is less than 1. Okay, so on down here. Now remember, if you need more practice, if more practice is needed, or you're wondering, well, where did we come up with this? Just let me know. Okay, so we've got 1 over 1 minus 2x. Well, that's a lot like 9a, except instead of x, we've got 2x. And we're expanding this about 0. But this one, whoops, this one is going to be n goes from 0 to infinity, 2x to the n. And as far as the radius of convergence, we're going to have 2n has to be less than 1. Or in other words, x needs to be between -1/2 and 1/2. So we have this radius of convergence 1/2. The interval of convergence is -1/2 to 1/2. We've also got the sign. Remember, it goes from n equals 0 to infinity, and it's going to be -1 to the n, x to the 2n plus 1. Remember, it's an odd function. And that's the Maclaurin series expansion for sine. The radius of convergence, it converges from -infinity to infinity. Now, cosine is like it. N goes from 0 to infinity. It's alternating, but cosine is an even function. Okay, now, so we've got these. These are basic ones that it's good for us to know. It's good for us to know these. And if we forget them, it's good to be able to just go back and derive them. So we could go back and derive these Maclaurin series, using the Maclaurin polynomial uh, framework. So now let's look at sine squared, sine x squared. Well, remember this is sine x. If we want sine x squared, just replace that x with an x squared. So it's going to look like this. We've got n equals 0 to infinity. We've got -1 to the n, but in place of x, we put x squared, and that's going to be x to the 4n plus 2. Nothing else changes. Yeah. And of course, e is another one. It's good to remember. it's just going to be x to the n over n factorial. Yeah, there are some power series. Now, let's do this. Let's take this right here, and we can see how we're going to use that to approximate an interval, a definite interval. In particular, we want to approximate this integral from 1 to infinity. I mean, I'm sorry, from 0 to 1, 0 to 1. We want to approximate this interval, sine x squared. That's what we want to do. And we want to do it so that the error, the absolute error, is less than or equal to 0.0001. Let's make let's make that our goal. Well, I don't know how to find the antiderivative of sine x squared. However, I do know that I could I could write that this way. I could say, well, this is the integral from 0 to 1 of this power series. N equals 0 to infinity, negative 1, x to the 4n plus 2 over 2n plus 1 factorial. See, we've already got that. We got that previously. Now I can get the antiderivative because we know how to get, oh, let me put dx. We know how to get the antiderivative. That just use the power rule for integration. So here we go. We've got n equals 0 to infinity. And I'm going to say, oh, let me put an n there. Negative 1 to the n. Okay, here we go now. X to the 4n plus 3. So yeah, add 1 and divide by it. Yeah, there it goes. And we're going from 0 to 1. So there's the antiderivative. Now, let me go ahead and use the fundamental theorem of calculus to, I'm going to plug in the 1, subtract, plug in the 0. When I plug in the 0, this whole thing is 0. So really, what we're looking at is this integral right here. N goes from 0 to infinity of negative 1 to the n over 4n plus 3, 2n plus 1 factorial. Now, what I need to do is I just need to start putting in values for n until I get to the point, and the absolute value now. I don't care about the alternating part of it. But when I'm trying to find the error term, what I'm going to do is I'm just going to start putting in values. I'm going to put in 1 over, let's see here, 4 times 1 plus 3 times 2 times 1 plus 1 factorial. I'll put that in. Then I'll try another one if that, and what I'm doing is I'm looking for the number that I can plug in to get something less than 0.0001. So the next number I try is 4 times 2 plus 3, 2 times 2 plus 1 factorial. I just keep trying these things. You know, you can use your calculator. And when you start plugging these numbers in, this one gets, you know, about 0.02, which is not what we're looking for. If you look at the next one where we put in a 2, let's see here. Ooh, this one gives 0.0007. Not exactly what we're looking for. So it looks like the next thing, the next value is going to be what we're looking for. So 4 times 3 plus 3 and 2 times 3 plus 1 factorial. It looks like that's what we're going to be looking for. So if I put in a 3, I get 0.00001. Ah, that's it. When n equals 3. So our approximation is going to be this. Our approximation is going to be n goes from 0 to 3. No, 2. 3 is our error term. See? Of, let's see here, negative 1 to the n. and over 4n plus 3, 2n plus 1 factorial. And there we have it. There we have our approximation for the integral.